I've avoided building DIY batteries from scratch because there just wasn't enough cost savings to warrant the effort and complexity to do a full DIY build. But now there's a happy medium ground. Companies are making kits like this one that Bass & Green sent me to build and test out. You can order grade A cells, build your own battery with significant savings, and end up with a professional product. When it's in stock, this case is only $550, and these 304 amp hour grade A EVE cells are only $106 each. That's 15.5 kilowatt hours for only $22.49, or 14.5 cents per watt hour. You can have factory build results with DIY pricing. I love it. Today, I'm going to take you step by step as I build this massive DIY battery and power it up, run a few tests, and see how it performs. Welcome back to Projects with Everyday Dave. Let's get started. Wow, this thing is huge. I don't know what I was expecting for 15.5 kilowatt hours, but I guess it makes sense. It would have to be fairly large. Even so, it's a really nice compact package. I mean, I can stand this up vertically next to the wall, and this is the tightest space of any of my other batteries. So this is going to be pretty awesome. It is heavy. I mean, just the case is pretty heavy. All right, I'm gonna have to build this pretty close to where I want it. So I think I'm gonna put a couple of 2x4s on the ground. I'll set them on it. We can assemble it laying down, and then I can stand it up against the wall because it's gonna be hard to move afterwards. And you can get a wheel kit for it that makes it easier to move around, but even with that, you know, it's gonna be a little bit of a challenge. All right, let's put this puppy together. Even better, I just set it on my hand truck. I can move it around, I can stand it up. Really easy solution to assemble on. Now, before I get started, I want to make sure I remove any jewelry that could come in contact with some of these connectors. We'll be assembling a very high current capable battery. And when we connect all of these batteries together, we'll be at 50 some volts with an unbelievable amount of current. So we don't want any unanticipated contacts happening. First, got to open the case up. A little magnetic tray is a great way to manage all the fasteners. Whew, there we go. Nice phenolic backside. All our bus bars, mounting hardware, insulators. Wow. That's nice. Everything's pretty much pre-assembled. Some more spacers, cables. The wiring and cables. Heavy duty bus bar. Good cabling. The ends are taped for the moment. The batteries come with their own insulating pads as well as additional bus bars, but these don't have a bend in the middle. The ones the battery comes with are a heavier duty bar, and they have a little relief in the middle, which is going to be a better situation. Those are beautifully packaged. Wow, look at those. Those are nice. Perfectly flat. No dents or scratches. Those are beautiful cells. Huge. Man, those are big. All right. Now it's time to stack them in. I printed out the battery indexing page for reference to make sure I get the positive and negative positions right as I go through, and I'm paying attention to that. All right, I got all the cells set out here, so it'll be easy to configure them and just quickly drop them in. I need to put the main protection sheets in. This is a massive amount of battery capacity. Loading all these batteries was like doing a mini workout. All right, that is touching, but it isn't tight. And I want to be able to put some pressure on these cells, provide a little pre-clamp load on there. So what I'm going to do is take some of the extra spacers that came with the batteries and add some space in there just to give me a little bit more compression on those cells. All right, the gap is totally closed now. That little piece of foam takes up, you know, a little bit of springy cushion, and the cells are super tight. Should give us good compression there with that plate on the front. They fit really nicely. I'm pretty happy with that. Pretty nice setup. All right, now I need to check the voltage of each cell and make sure they are within 20 millivolts of each other. 3.292, 3.292. Wow. These are all within 1 millivolt of each other. That is amazing. No problem. All right, now we can put on the BMS management, just connected to the battery hold down bars. And we can put the bus bars on, and these ones are super nice. They're very thick, slotted for the bolts, and they're not solid through the middle. They're actually completely flexible. That will allow thermal expansion and contraction without putting load on the fasteners. I love these. These are really nice. I'm going to leave the main connecting bus from pack 1 to pack 2 disconnected until I'm finished. That will cut the voltage I'm working around in half. Now, each negative post gets a BMS sensing wire. And the insulation, the heat shrink on these is really close to the nut landing surface. So you got to make sure that the nut doesn't get seated on top of that insulation. Now, the posts for these batteries can only handle up to 8 Newton meters of torque. If you torque them beyond that, you could twist the post in the battery and ruin the cell. So to give some margin, I'm going to use 6 Newton meters, which is what Basson recommends. And to make sure I get it exactly right, I'm going to use this digital torque wrench. Okay, now I'll go ahead and put the side-to-side bus on. Now, a couple of these terminals, the glue came off of them, presumably in shipping, so I'm just going to take some hot glue and secure those up just for good measure. All right, now I can check the pack voltage. Let's see what we got. 52.67. All right. Let's get the BMS put on and close this thing up. All right, now I can put BMS back in. All right, and it might have been easier to set this cable before I put the BMS on. Okay, I really like how those hang out in there. This one has a nice protective sleeve on it. Where's the protective sleeve for this one? Just gonna put some electrical tape on there to sturdy that up. There, I feel better about that. Okay, put a little zip tie on there for good measure. All right, now I need to connect the temperature sensors, which I should have also disconnected before I put this in here. All right, we've got 4 temperature sensors. We're going to spread them out around the pack. We've got high temperature tape to hold them down, and then I'll probably add a little hot glue just for good measure. You know what, just for good measure, I'm going to run some Capcon tape over the terminals so that wouldn't have to risk shorting something out. All right, the temperature sensor wires are all secured. I used some hot melt glue to secure them in 4 locations spread out throughout the battery, and then routed them back neatly so that I don't have wires going where they shouldn't be. Now I've confirmed that the voltage is 52, a little over 52 volts. I'm going to start with the negative lead, which barely reaches for some reason. Wow, that is tight reach. Really? This is a scary part. We're going to connect it up. Okay. Then we have the positive. And then this is the only positive lead for the battery sensing connections. Whew, no shocks. That's good. Okay. All right. Confirmed everything. Let me double check that we're getting our 52 volts here. No. Oh, well, that's going through the BMS, isn't it? 52.7. Okay. All right, now I think I can connect power to the BMS. And moment of truth. Let's see if it turns on. Ooh, power. Look at that. 52.68 volts. Well, now we can set it up, put the lid on, and man, that was pretty easy. Just a real quick pan here. All the wires connected up. To test this battery, I'm going to connect it to my Victron system. In order to do that, I'll plug in the supplied USB to RS45B port here. And then that will just connect directly to my laptop. Then I just have to turn on the unit, load the software. The software recognizes the BMS. I can see the voltage of every one of the batteries. Then I just select the appropriate menu, change it to Victron communication protocol, and then send that to the BMS. The BMS resets, and now we should be able to connect it to my Victron system through the CAN bus. Now I have everything protected within here, and there is a insulation layer on the lid itself, which is great. Not all of the battery systems have that, but you still do have to be careful not to hit the terminals when you put the lid on. That would be bad. All right, I can secure that, and because I have it on my little trolley, we can roll it over and replace my other pack of batteries. All right, it's 5 a.m., so I don't have to worry about solar coming in. I can go ahead and disconnect the solar input. Now I'm going to turn off the breakers for my current battery and disconnect this battery from the system and replace it with the Bass and Green setup. This is a good time to disconnect it because it's been running all night. I'm down to about 65%, be a good storage level for the battery. Nice to have breakers so you can just turn it off at the battery. Okay, I've got an alarm. The system recognizes the battery has been disconnected. It's switching over to grid power and maintaining all of the lights. These lights are plugged into this system so you can see they didn't even flitter. Yes, I hear you. I know. I did it. Now I need to shut the system down entirely so that I can make all the connections, but I will not make the final battery connection until we make sure that the capacitors are charged back up. So I'll go over that detail at that moment. Since the battery doesn't have a breaker, I'm going to use this breaker in a double configuration, which will allow me to have a 200 amp limit for my connection and be able to quickly and easily disconnect the battery. It also gives me a little bit more overcurrent protection. I'm using 2-aught cables since we'll be pulling up to 200 amps. All right, now we can connect the battery up. The breaker's off. I can make up my connections. I'm using 2-aught cable for everything. Now, this is just for testing. Don't give me too much grief about it. This breaker should be in its own box with a little cover on it so that you can't have access to these exposed terminals. And I would be standing the battery up to the wall and chaining it to the wall in case there was some kind of an earthquake or something, and putting some spacer underneath 2x4s to hold it up off of the floor. But we're just running testing here, so I'm not too worried about that. Also, if it was a permanent setup, we'd want to limit the length of our cables as much as possible, because more cable is more resistance is more heat, and that's just wasted energy. So I'll connect my negative terminal up first, and these terminal lugs, they're really nice. I didn't see a spec for the torque for these, but probably somewhere around 9 Newton meters would be sufficient. The kit also comes with these little terminal covers. They're not super robust, but they'll work. I really like these silicone ones. I'll put a link in the description for them. Just make sure I put it in a way that this bracket can't contact it. In fact, I might as well just use this one. Just don't want to block the display. All right, and finally I can hook up the CAN communication. All right, now I can power up the inverter and the BMS. We're still not actually connected, but that will allow us to confirm communication with the inverter. And a little trick that I told you before, I'll show you that the voltage between the positive and negative is actually around 50 volts from the inverter side. Because with Victron inverters, if you have them connected to grid power, they will pre-charge the capacitor for you and you won't need a pre-charged resistor at all. Otherwise, before we connected this breaker, I would need to cross these terminals with a pre-charged resistor for about 10 seconds, to make sure that the capacitors were charged up before we flipped the breaker. Otherwise, I would put a tremendous amount of current through the system very quickly. I can measure the inverter side voltage, and it's at 44, 45, 50. So the inverter's holding 50 volts on the terminal, so I don't have to pre-charge the resistor. Right, we have some configuration to do on the Victron side, but I should be able to flip this breaker now, and we should have battery power to the inverter. So let's see. And there it goes. Look at that. 13 amps, 14 amps. Man, I love it when things work. I flipped the switch and it powered right up. That is great. Okay, let's see what kind of power we're running here. All right, it's reading the BMS, so that works. It sees the battery being at 49%. We're pulling 700 watts, 14 amps, 52.4 volts out of the battery, running AC loads. There's no PV on right now because it's early in the morning. We did that on purpose. So now we'll run a few tests. I'll charge it with PV. We'll run it all the way down. I'll charge it all the way up. We'll check the capacity. We'll check some of the loading. I don't know if we'll get all the way up to 200 amps, but we'll see and see what this thing can do. Man, that was actually pretty easy. I mean, it took me less than 2 hours to build the battery and get it hooked up, probably even including film times. So this is pretty easy for a DIY battery. I mean, you get the cost savings of pretty much doing everything yourself, but it's pretty much already all done. You just have to do a little assembly. So this is a pretty neat way to go. I need to make a quick modification to the BMS settings. This BMS came programmed for 280 amp hour cells, and mine are 304 amp hour. In the BMS software, I click on Config, enter the password, which is 888888. Now I'm able to modify the basic settings. I need to change the full capacity setting to 304 amp hours and hit the right button, and also change the nominal capacity to 304 amp hours and hit the right button. Then I can click the read button to make sure the settings were applied, and I can see they were. If I go back to the info screen, I can see it's now updated to show the full and remaining capacity, and now everything is set up and ready to go. All right, go big or go home. Let's start with trying to run my 4-ton heat pump. Now, I've installed a soft starter from Active Start, which dramatically reduces the startup current. Otherwise, the 3000 watt inverters would have no chance whatsoever. But it will still be a significant load at startup. I turned off the grid connection. Now I just need to turn down the thermostat. Water pump turned on. Active Start's firing up. There it goes. It started right up, no problem. Typically, I would need more than one battery for this type of load, but this battery has a 200 amp BMS, which allows it to do a lot of things that you would normally need several batteries for. So this is really successful. I'd say if it can start this up, I'm gonna have no problem with most things in the building. Well, I'll let it run for a while just to see how it does, but the hardest part is starting it up, so I'd say that's a success. I used my Victron home backup system to do a capacity test on the battery. This system is capable of 120 and 240 volt and maintains all of my emergency circuits. Those are my fridge, my well, my microwave, TV, modem, security system, and some lights around the house. By the way, I have step-by-step instructions on how to build this off-grid solar-powered system, and I'll leave a link to that in the description and at the end of this video. I started the test at 100% state of charge, which was 54.14 volts under a little bit of load. It took almost 32 hours to drop the battery to just under 20% capacity, which is a typical stopping point if you're trying to extend the life of your battery. Then at about 40.7 hours, the BMS cut the power at 8% capacity, or about 280 amp hours. A picture of the BMS menu shows a voltage of 50.48 volts. So under load, it probably dropped below 50 volts. That's a very nice result. I was able to power my emergency systems for more than 1.5 days with no solar input. I was able to use 14.6 kilowatt hours of the 15.6 kilowatt hours of available capacity in these batteries, or 94% of the total capacity. You can see from the graph of forecasted solar input, there would have been 2 opportunities for solar input during that time to recharge the battery. But this was just to show how much we could get with no solar input. Running my entire off-grid system with this 15 kilowatt hour battery for the past week was no problem. I used my 3200 watt firewood rack solar array for the input. You can see I had a very sunny day right after my complete discharge that was able to charge the battery back to 100% in one day. We had cloudy or rainy days the whole week, but the battery never dropped below about 60% capacity. So it's easy to see how a 3.2 kilowatt array and a 15 kilowatt hour battery would work fine for me, at least in the summer months, to put all of my emergency systems completely off grid. But of course, you know from my previous videos that even my 25 kilowatt hour battery wasn't quite enough for the cold, dark month of January. This build was a lot of fun, and it wasn't that hard to do. It performed flawlessly. There are a couple of areas for improvement. The software was not terribly user-friendly, and I would have preferred to have a breaker built into the unit instead of having to apply my own externally. If I can get you any discount codes on the materials I used in this video, I'll leave them in the description below. I'm going to join this unit up with the rest of my battery capacity and let it run over the next year or so and see how it performs, see if there's any problems over the long term. If you want to see step by step how I built this off-grid solar powered system, you can check out these videos right here, or check out my website, projectswithdave.com, where I have lots of other projects on solar power and battery backups, as well as a free calculator to help you determine if solar will save you money. Thanks for watching, and I'll see you next time.